Okay, in this second item on the exam, we've got a cantilever beam that we are extending in this industrial situation to help support additional equipment associated with a product line. And a senior engineer has decided that what we're going to do is create a hinged connection here and then take that beam on over and connect it to a steel column with a web-only connection. So we in effect have a roller or a pin type situation here, a hinge in the middle, and then the original fixed in for the cantilever kind of situation. We're asked to predict the shape of the moment diagram and indicate critical features of that diagram that we should expect from the computer model. So for instance, some of the things that we could note right off the bat is that of course W, our uniformly distributed load, is a constant. And since the second derivative of the moment is going to be equal to W, that means that we should end up with a second order moment diagram throughout the entire beam. Another aspect of this is that we're going to have moment equal to 0 here at the hinge, as well of course we'll have moment equal to 0 at the row. Oh wait, it won't be equal to 0 here because we have an applied couple right there. So we know that the moment won't be equal to 0, it'll be equal to a minus 5 kip foot frowny face here at the end. And then we'll have some non-zero moment here over at this end. Now it's tempting to think that it would probably be negative, but we got to be a little bit careful about what's going to happen here, and that is there are two competing effects going on in this particular situation. One of them is just from the distributed load, which is going to want to cause the beam to try to sag downwards and create a deflected shape that might look something similar to what we see here, and we'd have some sort of smiley face portion here. So frowny face over here, smiley face. This is all caused by the W load, all second order moment diagram, a fourth order in terms of the actual shape of the deflection, transverse deflection. Now this moment though that's being applied is going to do quite the opposite, right? It's going to want to try to rotate this end, not try, it will rotate this end in a clockwise fashion, popping up this middle segment that's now going to have to bend back the other way in order to then get back to our support. And so for that situation, then we'd have a deflected shape that might look something like so. Grossly exaggerated, of course, and I don't know which one's going to win out. And because of that, other than these general things about the shape, I don't have a lot of choice here. If I want to get anything more precise, I've got to go try to do a little bit more work. And in this case, that work is going to be actually pretty straightforward and easy. And that's because we've got R equal to 3 at the left and R equal to 1 at the right. So the total number of reaction components then would be the sum of those two, that's 4. We have then N equal to 3 equilibrium equations plus 1 special condition, that's the hinge, so a total of 4 conditions of equilibrium, for which then this is a statically determinate structure. And that means I can go find what the reactions are just with the equations of equilibrium alone. And I can draw the shear diagram and I can find out exactly what's happening with the moment diagram. I probably can actually, just from getting the reactions, figure out what the rest of this thing is doing overall. So let's break it at the hinge. That's always the key thing when we've got a hinge. Break your structure there. We've got then the distributed load at a half a kip per foot, and then we'll have a vertical reaction here, Cy there. We got the imposed load of 5 kip foot at the far right in a clockwise fashion. We'll have the shear at the hinge, and then that gets reflected around, of course, being an internal effect. And we'll have then, of course, the distributed load. We'll have a reaction that presumably, given if everything acts in the way I've got shown, then AY has to be going up. And my supposition is that we'll end up with a counterclockwise moment at A by the time we're done with all this, right? Or a negative moment. Let's see how it might all play out. Let's find what the shear at B would needs to be. Okay, so we'll take sum of moments about point C just for that right-hand free body diagram. We'll take clockwise as positive, so we'll have a plus VB times then the 10 feet for the moment arm, and then the load is going to be a half a kip a foot per foot, that is, times 10 feet times the moment arm, which will be 5 feet. Ooh, that's a minus. So keep track of this carefully. And then plus the 5 kip foot, that's going clockwise. Set that all equal to 0, and what are we going to end up with? We've got a 0.5 times 10 times 5, subtract off the 5, that gives us 20 divided by 10. That tells us that V is equal to 2 kip feet, well, I'm trying to go too fast here, 2 kips acting in the direction as shown on that free body diagram. 1/2 kips per foot times 10 feet would be a total of 5, so 5 minus the 2, that means CY is going to be 3. And since we have verified the direction of the shear on either end, then that means I am going to be right that M sub A is going to be acting in the direction as shown. So some moments about A, and we'll get then M sub A itself minus 0.5 times 5 times the moment arm of 2.5, and then minus the now 2 kips times this moment arm of 5 feet, set it equal to 0, and therefore find out that MA is acting, well, that's 10, that's a half of 12.5, that's going to be 16.25, I think. Let's just make sure. That's 10 plus 0.5 times 5 times 2.5, yep, 16.25 kip foot acting in the direction shown. Right, so that tells me that then the moment diagram is going to, I'm going to skip the shear diagram here for a second, go straight to the moment diagram shape, and then come back and check a couple of things. Right, one, we know that we need to start off at minus 16.25. We know that it's second order in this location. It's supposed to be 0 at point B. Continue second order, maximizing somewhere out in here, and then it's going to keep coming down. It's going to be parabolic coming downwards, and it's supposed to end up at minus 5. So it's going to be a second order curve that looks something like that. That's my guess, right? And that's a pretty good guess. We can do a little bit better. It doesn't take much to then just go get the shear diagram to begin with, and then we could get numbers on this thing. Right, that's in kip feet. This is in kip. And so the shear is going to pop up by AY. Alright, so AY has to be then equal to, opposing these two, so 2 going down plus that 1/2 times 5, that's 4.5 going up. And then it's going to come down by 1/2 over the, it's going to come down to 2, which is exactly what it should be right at point B. And then it's going to keep on going in a nice, hey, dV dx equals the distributed load magnitude, and we're going to end up at minus 3 all the way out at that far right side. How do I know? Well, it had better be because of the reaction that's there, but how do we really know? Well, again, 4.5 minus 0.5 times 5 will take us to 2 right at point B, and then we know we go 10 times 0.5 negative as a change, so negative 5 down to there, bam, that's really the way it works. The similar triangles that we end up with here, then that's going to be 4 foot and then 6 foot to get to that point, to the point of 0 shear. If you go find then the area of that, right, so that's the average of 2 and 4.5 for that trapezoidal height times 5, bam, 16.25. You add it to negative 16.25, and we really do get 0 moment, just like we're supposed to. This is 4 foot, so 1/2 base height, 1/2 of 2 times 4 is the same thing as 2 times 2, so that means that we're going to end up with then a maximum moment of 4 kip foot right there. And so that was 4 foot by symmetry. That's got to be 4 foot. That's 2 foot to get us to then that location of the inflection point. And